All right, good morning, students. This video is going to be an instructional video on the use of a micrometer, as well as how to calculate thickness variation. This is something that we have been discussing in class and practicing in class, but since we are now in an NTI format, I wanted to make this video to try and reinforce or help anyone who may still be needing some additional practice in that area. So I'm going to use a couple of different things. I created a cheat sheet and I posted a link to that on the classroom stream section, and that is just a hand-drawn sheet of paper where I broke down the different components or different parts of a micrometer and what all the little numbers and markings represent. So we're going to go through that, and then I also developed a presentation that I'm also going to link on the calculation of thickness variation. So it talks about what thickness variation is, how you find it, and then how you can potentially be able to correct it, which goes along with our brake lathe instructional video. So I'm going to share those pieces of information with you now. So the first thing that I want to share is all of this information is going to be linked here in our stream section. So I went ahead and linked the video here for the brake lathe demonstration. Make sure that you're checking this every day. And then here's a link to that cheat sheet right here. And then I'm also going to be providing a link to this document. So, working our way through each of these. Oops, hit the wrong button there. That's not what I wanted to do. This is what I wanted. So, how to calculate rotor thickness variation. Number one, what is rotor thickness variation? So thickness variation is also referred to as parallelism. Depending on what text you're reading, what test or quiz you're taking, it may be called both of those things. So you might see one question in regards to thickness variation, and then 3 or 4 questions down see something about parallelism. They're the same exact thing. Rotors become out of round over time. That's the term that I often will use. Rotors get extremely hot, then they get extremely cool. So what this means is that they have high and low spots, and this can lead to a common concern of brake pedal pulsation or steering wheel shake when the driver steps on the brakes. Very, very common complaint. The official term that is used to describe this in any text standard or textbook is going to be thickness variation or parallelism. These are interchangeable terms. To determine what this is, what this number is, you must first be able to accurately read a micrometer. Okay, so a micrometer, an inch micrometer, is what we're going to use here for this example. So a micrometer is a tool that is used to measure OD, or outside diameter. There are also tools used to measure height, inside diameter, depth, but for this demonstration, we're just going to focus on the standard outside micrometer. These come in both standard and metric, but we are going to focus on the use of a standard inch micrometer, and the reason being is if we have a vehicle that has a metric reading in millimeters, we can just use basic math. There's 25.4 millimeters in 1 inch. So 1 inch is equal to 25.4 millimeters. So if we want to convert between the two, all we have to do is use either multiplication or division, depending on which way we're trying to go. And as long as we know that there's 25.4 equal to 1, then we can find the numbers that we need just using that basic math. So there's not a need to go out and purchase dedicated metric tools when you can just use a calculator. All right, so here is that cheat sheet, and you have a link to this as well. You can print it out if you'd like, but this just gives a simple breakdown of what all the little markings on this mean, and it's difficult for me to show you this on a video. Zoom in here, or you can see what these are, but this is just broken down on a piece of paper. So first thing, we go down here to the bottom of the page, and on the bottom of the tool here, it's 1 to 2, and then it says mic scale. So the micrometer scale, what that is that is the minimum and maximum that this particular tool will read. So if you have a tool that's 0 to 1, that means that it will measure from nothing, 0, all the way up to 1 inch. If you have 1 to 2, that means that the base unit of measure is going to be 1 inch. So every measurement on this tool, since it's a 1 to 2 inch scale, is going to start with a 1. The highest that it could possibly go is 2.000. These tools are accurate to 1,000th of an inch. So pretty much all of your measurements are going to be 1 point something, something, something. So we have two different things that we need to look at. We need to look here. This is referred to as the barrel. Some people refer to it as the sleeve. The barrel or sleeve is the part of the tool that does not move. So this stays stationary. It never rotates. The thimble over here is the part that you're turning with your fingers to tighten up or clamp down on the component that you're measuring. So first, let's look at the barrel or sleeve. The barrel or sleeve has two separate measurements. So first, let's talk about money. If you can count money, then you can read a micrometer because they're based on the same type of or thought process of measuring. So you have, in terms of money, you have a whole unit, which would be $1. And in that dollar, you can break that dollar down into different segments. So the easiest way to break a dollar down is in 4 quarters. You take 4 quarters, that equals $1. So if you have 4 quarters, most people would much rather have a single dollar bill. So you take your 4 quarters to the bank, you trade that in for a piece of paper. Now, you can break that down even further. 1 quarter is equal to 25 pennies. So if you have 25 pennies, that's a whole lot of little items. You take that to the bank and you exchange it for a single quarter. If you have 100 pennies, then you are equal to $1 as well. So thinking in that terms, this can be broken down the same way. On this barrel or sleeve, we have these whole numbers, 0, 1, 2, 3, and it goes all the way up to a 9. So if we counted this all the way out, it would continue to go all the way up to the 9. In between these whole numbers, we have these little lines or markings. So each one of these whole numbers represents $1, or in terms of a micrometer, it represents 100 thousandths of an inch. So we have 100 thousandths, 200 thousandths, 300 thousandths, and if we kept going, we'd have 400, 500, 600, 700, 800, all the way up to 900 thousandths. Now, 100 thousandths looks like this if you write it out on paper, 0.100. So 200 would be 0.200, 300 would be 0.300, and so on and so forth. 500 thousandths is equal to half of an inch. Now, all of these lines in between represent the quarters. So in between each of these, you have essentially 4 lines. Once you get to the 4th one, you're on the next whole unit, or 100 thousandth. So each one of these lines represents a quarter. A quarter is equal to 25 thousandths. So 25 thousandths is 0.025. If you have 2 of these lines, it's 25 plus 25, which would be 50. If you have 3 of these lines, it's 25 times 3, which would be 75. Once you get to the 4th line, you now have another whole, or 100. So when you are reading this tool, it's important for you to understand what all this means. Now, the part that you're turning with your hand is referred to as the thimble. And the thimble is what's going to have your single units, your pennies. So the thimble is marked like this. It usually goes in increments of 5. So we have a 0, and then we have 1, 2, 3, 4. Once we get to the 5th one, we have a larger line to make it easier to read. And then once we get past the 5, we would have 6, 7, 8, 9, and then when we had 5 more, we would have a large 10. So when you are reading this tool, you have to pay close attention to if you are before or if you are after this 0. Because if you are after this 0, that means that you have went past or surpassed that next marking here. So you're going to have 25. If you're before the 0, then you're going to be somewhere in between the 0 and the 24. So It's very important to understand how to use this tool in order to have accurate readings. The whole purpose of using the accurate tool is to be accurate within a thousandth of an inch, which is a single unit. Okay, so calculating thickness variation is pretty simple. We are going to take a brake rotor and we are going to measure it in 6 locations. And I'm going to do that for you here in just a second. So you are going to take these 6 measurements and you're going to compare them. If a rotor is good, it will have approximately 5/10,000ths of an inch or less variation, which is virtually nothing. And that number is right here, 0.0005. So that's less than 1,000th of an inch. Most rotors that are used will have anywhere from 1 to 5,000ths of an inch variation, which is extremely excessive in most cases. You would take your highest measurement, which would be your thickest measurement, and your lowest or thinnest measurement. You're going to take those 2 numbers and you're going to use subtraction to find the difference between the 2. The difference between the highest and lowest number is going to be what your thickness variation is. And if it's anything in excess of 1,000th of an inch, for the most part, it's going to be too much. It's going to lead to that pulsation problem. Now, the correction. What do you do about thickness variation? Well, you have 2 options. Option number 1 is that in most cases, these can be machined. These rotors can be taken off and they can be put on that brake lathe, as long as they are going to be reusable. So first thing that you have to do before you decide if you're going to machine a rotor is you need to figure out what that minimum thickness is. So you're going to look at the manufacturer's required minimum thickness. If the rotor is above this number, then it may be able to be machined. If the rotor is at or below this number, then you cannot machine it. A rotor that is too thin cannot dissipate enough heat. Rotors that are below this spec should be discarded. You throw them away. If a rotor is right at the spec or slightly above the spec, then you can put it back on the car. So you explain that to the customer. You say, hey, we can't machine your rotors. They're going to be below minimum thickness. So you can either buy a new set of rotors, or we can just put these rotors back on your car, which is not optimum. You don't want to put brand new brake pads on a set of used rotors. A rotor should be approximately, and I say approximately because every manufacturer has a different specification. GM has one spec, Ford has one spec, Toyota has one spec, but in general, they're all going to be around or approximate 30,000ths of an inch. So if you're going to machine a rotor, you need to be approximately 30,000ths above whatever that minimum thickness is. And the reason for that is you need to leave room for normal wear and tear as the brakes wear down. Okay, so let's move on to our actual demonstration or example here. So what I have is just got this untitled document here, and you should be able to still see me. So I've got this document. We're going to use this as our 2 different examples. This. So we have a brake rotor, same brake rotor from a previous video. So the information that you're going to gather off the vehicle that you're working on is going to lead you to these vehicle specifications. Sometimes they will be printed or stamped on the rotor. So just glancing at this one, if it's stamped in the rotor, you'll usually be able to find it pretty easy. This one does not appear to have any stampings or markings in it. If it does, it makes the process even simpler. But this one does not. So we're going to look that information up. So this rotor is off of a 2003 GMC Denali truck. A Yukon or a pickup truck would use the same brake rotor. So we're going to use all data to look this information up. So we'll set this down for a moment, and we will go to the All Data website. All Data is just an online service manual. So we're going to click right here on Repair. Okay, make sure we're still presenting. And we're going to go through our year range here. So I've actually already looked it up, but I'm going to show you through it step by step. So 2003 is the year model of this vehicle. And now the make, GMC is who makes the Yukon. And now we're looking for the Denali option. So this is actually a Denali Yukon, but they don't offer that option for whatever reason. So we're going to go down a little bit further, and we've got Sierra Denali. So there's a Yukon Denali, which is the SUV, and there's a Sierra Denali. They're the same vehicle with the exception of one's a pickup and one's an SUV. They're both all-wheel drive. They both use the same engine. They both use the same brakes. Okay, so we are going to select that option. Now, this is all alphabetized to make it fairly easy to navigate. So we are working with a brake rotor. So we're going to go to the brakes section, brakes and traction control. And we are working with disc brakes. And we are working specifically on the brake rotor right here. So we got brake caliper, brake pad, disc rotor, brake rotor. So we're going to click on that. And it's going to give us the options for specifications. Okay, so if we go back a little bit, we've got disc brake rotor here as well. So this is just for technical service bulletin information. We want the mechanical specifications for this rotor. So here, it's going to give it to us in both millimeters as well as inches. And it tells us we have two different options. We got JC3, JC4. So these are both the same in terms of the size of the rotor. And we've got another one here for front brakes, which also is the same. So sometimes you'll have different vehicles with different size brakes. So here we've got one that's substantially larger. So you need to know what specific rotor your vehicle has on it so that you can make this determination. All right, ours is going to be this one up here. So we have the rotor minimum allowable thickness after refinish, and then we have the rotor discard thickness. So we have two different measurements here that we need to be aware of, and this has a little asterisk or star next to it. So the rotor thickness new is this, 29 millimeters or 1.14 inches. That's 1 inch, 140 thousandths. The rotor's minimum allowable thickness after refinish is 28 millimeters or 1 inch, 100 thousandths. So you can see there we have a 40 thousandths of an inch tolerance, which is pretty close to the 30 number that I gave you. All right, now we have our discard thickness. So that means that if it is at this number or below, if it is at 27.5 or below 27.5 millimeters or 1.082 inches, the rotor needs to be thrown away. So we have a variance here that we can play with, which is just barely around 20 thousandths of an inch. So if the rotor becomes thinner than this, we really don't need to be machining it because it's going to become too thin. So let's go over here to our example. So the rotor's minimum thickness, in our case, we look here, the discard thickness, that's going to be your minimum thickness, is 1.082 inches. I'll put discard at 1.082 inches. So anything thinner than that, throw it away. So now, let's say that we're measuring our brake rotor. And got my brake rotor here. So we're going to measure it. Okay, so this would be measurement number 1. And all of our measurements are going to be 1 point. And I've got the number 1 visible, so that would be 100 thousandths of an inch. And I have 1 line, and I'm not to the second line. So 1 line is 25 thousandths. And then I'm going to look at my thimble, and I'm sitting on the 17. So if I take 25 plus 17, that's going to give me the last 2 digits. Okay, so if we do that over here, 25 and 17, 25 and 10 would be 35 plus an additional 7. So we just come over here Just trying to break this down for our first measurement. So we've got 1 inch, and we have 100 thousandths. Okay, then we have 1 line, which is 25, and then we have our barrel measurement, which is 17. All right, so we're going to add all this stuff together. So we're going to have 1 plus 100 plus 25 plus 17. All right, so if we take 5 plus 7, that's going to give us a carryover factor if we do it up here. All right, so let me see if I can draw a line underneath of this. And you could, of course, do this on a calculator, but I'm trying to show you how to do it on paper. So you add all this together. And our first measurement is going to be 1.142. All right, so in that one particular area, that's what the rotor measures. So if the rotor's in good shape, then it should be this same dimension plus or minus 5/10,000ths all the way around the rotor. But what we're probably going to find is that it's not. It's probably going to be excessive. So now let's measure it in a different spot. Okay, so measure it here. And it's a significant difference. So we have that same 1 line and the 100, but we're sitting on the 7. So we have a 10,000ths of an inch variance measuring the rotor 180 degrees apart. So this measurement here is going to be 10,000ths of an inch less, which is a whole big number. All right, so we're going to have that same 1.1, and then we have 1 visible line. 1 line is going to represent 25, and then we're going to add 7 to it. So 25 plus 7 would be 32. All right, and then we would continue to measure on around the rotor. So let's measure it a little bit over here. Okay, this one is actually the same. So 1.132. Measure it over here. Okay, this one is about 2/1000ths of an inch bigger than that. So 1.135. Right, that one is just a little bit bigger. 35. Okay. So we've taken all of our measurements. All right. Now that we have all this information, we're going to take our highest number, and our highest number, put it over here. And our lowest number. And it looks like our lowest number was 1.132. And that's an easy number. So we have a difference there of 10,000ths of an inch. So that means that our thickness variation is 10,000ths of an inch. Now what that tells us is that we have at least 10,000ths of an inch that we're going to have to remove from this rotor in order to make it straight. Now in reality, it's probably going to take more than that because we're cutting a circle. So if you're cutting that material off, you're going to have at least 10 thousandths removed to make the rotor smooth, and then you're going to have a finish pass as well. So we'll just say 12 thousandths of an inch is what it's going to take to make this rotor straight, true, and smooth, because the finish pass is going to add at least 1 notch, which is 2 thousandths. So if we did a fast cut and we removed 10 thousandths, then that would be, you know, the rough cut on the rotor. Then we would have to do a slow cut to clean it all up and make it smooth again. So what we now have to do is we have to see if we have 10 thousandths of an inch to play with. So we have this 1.132, and then our discard thickness is here. So we definitely have at least 12 thousandths of an inch variance. So in this example, the rotor can be machined and reinstalled because we have enough. Now, let's say, for instance, that we have that same number and we get measurements like this. 1.100, 1.101, 1.099, 1.098, 1.101. And these are just examples. Okay, so in this example, we're using the same rotor, but let's just say these are our measurements instead of the actual measurements that we got. So we have our highest, which would be 1.101, and then we have our lowest, which is 1.098. Okay, so in this scenario, our rotor is much closer to our actual discard dimension. So what we have to be careful of is, if we look back over here at all data, it tells us that our minimum allowable thickness after refinish is 1.10. So if we look at our numbers, if we look at our first example, we're not going to be below that number if we remove 12 thousandths of an inch, because if you subtract 12 from 32, you're still above that 1.10. But here, we're riding right on the line. 1.10 is really about as thin as you want to be, so that you're still above that discard dimension. So here we have a variance of about, 3 or 4 thousandths of an inch. So if we remove 3 or 4 thousandths of an inch from the rotor, it's definitely going to be underneath of that number. It's still going to be above our discard thickness, but we can't really machine it and clean it up to put it back on the vehicle. So in this example, the rotor cannot be safely machined and reinstalled. We don't have to discard it, but we can't machine it and put it back on the car because it's going to potentially lead to issues. Okay, so looking at these two examples, hopefully that gives you a better understanding of what it is that we're trying to achieve when we're looking at this variation. All right, so if you get numbers like this first example, then you're good to go. You can machine the rotor, you do your fast cut, your slow cut on both sides, you put it back on the car. If you run into a situation here where you're right on that borderline, or you actually start to fall underneath of that borderline, then the rotor cannot be machined. Your only options are to put the rotor back on the vehicle, or you try to talk the customer into buying a new set, because that's really the best option anyways. All right, so hopefully this gives you a very good, knowledgeable understanding of, number one, what thickness variation is, what that actually represents. And number two, how can we find thickness variation by using manufacturer specification and a micrometer. And then lastly, leading up to the machining, the actual turning or cutting material off of that brake rotor. You have to first establish, is it going to be worth the time to do that? To do a brake job and machine a brake rotor on both sides, you're generally talking about an hour to an hour and a half, depending on the vehicle. So are you going to be coming out ahead if you're going to be machining the rotor? Is it going to be worth it, or is it going to be a waste of your time because you fall underneath of that number and then have to discard? All right. If you have any further questions about this, please let me know. We're going to continue to practice this in the lab once we are able to come back. But up until that point, the best that we can do is these videos. And if you have questions about these videos, please let me know. If there's anything that you'd like for me to add to the videos, if there's anything that you'd like for me to go more in depth with as far as micrometer reading goes, or the operation of the brake lathe. If you have suggestions or comments, please let me know, and I will do another video, or I will make a supplemental video on adding those details that you may want to see or hear about. Hope everybody has a good day and a good afternoon, and I'll see you in the next one.